Next, after learning about the general forms of the solutions to some certain kinds of recurrence relations, next we're going to learn about how to define this formula if you are doing it with a decimal number or a fraction or even an irrational number. So let u be a real number and k a non-negative integer. Then we're going to define u choose a 0 as equaling 1. And we're going to define u choose 1 as equaling u divided by 1 factorial. We're going to define u choose 2 as equaling u times u minus 1 divided by 2 factorial. I should probably write it like this, actually. And then u choose 3. Okay, so do you see the pattern? Tell me what u choose 3 would be. What would u choose 3 be if I just continued the same pattern of u? It'd be u minus 1, and then it'd be u minus 2. So when you do u choose 3, there's 3 factors that are done. And then it's 3 factorial on the bottom. How does that look to you? So this actually works anytime that u is a real number, which means it could be a decimal or it could be an irrational number like pi or anything. And then it just keeps on going like that. That's the pattern. So once we know that formula, the formula for n choose r can be expanded to something for u choose r, where u is any real number. And once we learn that, then there's something called the extended binomial theorem. Extended binomial theorem. And it just says this: the 1 plus x to the power of any real number, which is really strange, equals a summation from k equals 0 to infinity. And now often there aren't an actual infinite number of terms in that, because many of the terms turn out to be 0 in some cases, but in other cases none of them turn out to be 0. But that's the formula. 1 plus x to the power of any real number is the sum from k equals 0 to infinity of u choose k x to the k. So the binomial theorem can actually be used for irrational numbers as well. So first, though, let's see if this extended binomial theorem works for an ordinary thing like 1 plus x squared. So let's plug in a non-irrational number into it, or a non-fractional number, or non-decimal number into it. See what happens. According to that formula, what would 1 plus x squared equal if I let u equal 2? 1x. Well, so make sure that you plug it in the formula. It'd be 2. What's the value of u? 2. So since u is 2, it'd be 2 choose k. And what's the value of k at the bottom of the sequence? 0. So it'd be 2 choose 0, x to the 0, plus 2 choose 1, x to the 1, plus 2 choose 2, x to the 2, plus 2 choose 3, x to the 3, and it'd go to infinity, right? Now that does now go back to college algebra. From college algebra, who remembers the formula for a plus b squared? The formula for a plus b squared is 1 times a squared plus 2 times ab plus 1 times b squared, right? 1a squared plus 2ab plus 1b squared. So let's see if we get that. So according to the definition of u choose 0, what is u choose 0 always? At the top of the page. What is u choose 0? 1. So that'd be 1 x to the 0th. And what is you choose 1 according to the top of the page? You choose 1 is u divided by 1 factorial, which is just u. So that just equals u. So 2 choose 1 is just 2. And then x. And then what is 2 choose 2? What would 2 choose 2 be according to the top of the page? 2 choose 2 would be 2 times 2 minus 1 divided by 2 factorial. What is 2 times 2 minus 1 divided by 2 factorial? 1. So we get 1 x squared. And then what does 2 choose 3 according to the top of the page? It would be 2 times 2 minus 1 times 2 minus 2 divided by 3 factorial. And what is 2 times 2 minus 1 times 2 minus 2? What is 2 minus 2? And so if you multiply by 0, what do you get? 0. In fact, all the terms beyond that will be zeros because they'll all be multiplied by 0. So there's actually only 3 terms in the expansion. So what we get is 1 plus x squared is equal to 1x to the 0th, which is just 1, plus 2x plus 1x squared. Now, if I go to the formula for a plus b squared and I put that in, it should be 1 times a squared, which is 1, plus 2 times a, which is 1, times b, which is x, plus 1 times b squared, which is x squared. So that when, if you multiply 1 times 1 squared, you get 1 plus 2, and then 2x plus x squared. So we get the same thing. So this is a more complicated way of getting the same answer. But this also lets you get answers that you could never do with Pascal's triangle, though, because Pascal's triangle only has integer values, like x squared, a plus b squared, or a plus b cubed, and things like that. But with this formula, we can actually figure out what things are, like what's 1 plus x to the 0.5 power. So let's go back and in fact, let's go to a new page. What is 1 plus x to the power of 0.5? In other words, what's the square root of 1 plus x squared? What is this? Okay, make sure you're watching, everybody. Okay, there we go. What is the square root of 1 plus x squared? Well, it's going to be the same formula, right? It's going to be, what is u? 0.5, yep. So it's going to be 0.520 plus, times x to the 0th plus, what's going to come next? 0.52 is what? What's the next number after 0? The next integer after 0? 1 times x to the what? 1. And then what's the next integer after 1? 2. And then x squared plus 0.5 choose 3 times x to the 3rd. And it keeps on going like that. Now, let's just calculate some of those values. 0.5 choose 0. Anything choose 0 is always 1. So that's just 1 x to the 0th. And then the next term, 0.5 choose 1, is going to be just 0.5 itself divided by 1 factorial, x to the 1st. The next term, 0.5 choose 2, is going to equal 0.5 times 1, 0.5 minus 1, which is negative 0.5 over 2 factorial, and then x squared. The next term, 0.5 choose 3, means it has 3 factors, and each of them is 1 less than the one before. So what's 1 less than 0.5? Negative 0.5. And what's 1 less than negative 0.5? Negative 1.5. And then it's divided by 3 factorial, and it's times x to the 3rd. And then you keep on going like that. So should I do one more term? Do you think you can see the pattern already, or should I do one more term? Let's do one more term. So let me erase the dot, dot, dot. So what would it look like if I went ahead and wrote out one more term of the problem? It'd be 0.5, of course, to start with. So then you'd have 3 more terms, so there'd be a total of 4. So 0.5 times 1 lower times 1 lower than that times 1 lower than that divided by 4 factorial times x to the 4th. And then it would just keep on going forever. So how long do you need to go until you stop? Good question. So it depends on how big the x is. So if the x is something small, like maybe 0.1, then x to the fourth power would be something really small, like 1/10,000. So you'd be accurate to 1/10,000th of a degree of accuracy once you got to the x to the fourth term. If you had really big x value, though, this problem wouldn't take a lot of steps to get an accurate answer. So this problem converges. That means how fast it gets the right answer. It converges fast with only a few terms if x is small. It does not converge very fast if x is big. So that's cool. But if you did it forever, though, you'd always get the exact right answer of what 1 plus x to this, what the square root of 1 plus x actually is. Okay, perfect. Let's go ahead and simplify those terms a little bit, though. So what is 1x to the 0th? What is x to the 0th? Assuming x is not 1. I mean, x is not 0. What would it be? Just be 1, right? And then what is 0.5 divided by 1 factorial? That'd just be 0.5. And then what is 0.5 times negative 0.5 divided by 2 factorial? That'd be negative 1/8, right? Because it's a half times a half divided by 2, which is negative 1/8. And then x squared, like that. So that's kind of cool. Let's just go ahead and stop with those three terms and try this out maybe on Desmos.com. So let's go ahead to this website. And I'm going to define one function called the S of x is going to equal the square root of 1 plus, or I'm going to just write it like this, 1 plus x to the 0.5 power. So that's technically the square root of 1 plus x, right? Then the next formula I'm going to do is called I'll just say M for method. This is or B for binomial. Binomial expansion of this of 1 plus x to the 0.5. The binomial expansion of it would be 1 plus 0.5 x minus 1/8 times x squared, like that. So there we go. Now notice that this binomial expansion starts out at x equals 0. So when x equals 0, the value is right here. So the binomial expansion problem is the blue line, which obviously you can tell the blue line is a parabola that opens downwards. The first three terms of the binomial expansion are parabola that opens downwards like that. And the binomial expansion of it is extremely accurate as long as you're close to x equals 0. In fact, it's perfectly accurate at 0, and it's almost perfectly accurate when you're close to 0. So whenever you do a binomial expansion like this, it's only accurate when you're close to 0, unless you add a lot more terms. So let's go ahead back to our whiteboard and maybe add one more term. So if I take 0.5 times negative 0.5 times negative 1.5 divided by 3 factorial, that would equal, it's going to be a lot, so that'd be 1/2 times negative 1/2 times negative 3/2, so that'd be 3 on top, 8 on bottom, and then 3 factorial is 6, so that becomes that, and then it'd be positive because you have a negative times a negative. So it'd be 3 over 8 times 6, the 3 goes into the 6 and leaves you 2, so you get 1 over that. So you get 1/16, I believe, x to the third. So that looks good. Let's add a 1/16 x to the third onto it. Oops, I said 16, my fault. Now, do you notice that now it stays closer to the line for a lot longer? In fact, well, I don't want to delete everything I have on, well, I guess I could. So I'm going to go ahead and delete everything I have on my whiteboard just so the people online will be able to see this. So share, place, there we go. So in fact, I'm going to write several of these actually. So I'm going to take that one and copy it, paste it, and paste it. So this is I'm going to call this in B1 of x. That's just going to be just 1. B2 of x, I'm going to call that the first two terms. And then B3 of x is going to be the first three terms. B4 of x is going to be the first four terms. And I guess I don't need B the next one. So do you see how that these different approximations from the binomial theorem are each closer to the graph of the function for a longer and longer time? So the red graph is the exact graph like that. The green graph is the straight line 1. Notice the straight flat line v of 1 of x equals 1. That's only one term of the sequence, so it's a constant. And it is exactly accurate to the function only at one point. And it's kind of close, but not very close for a little bit. But then it's very far away from it. Very, very far away from the correct graph. But the line that has 2 points, the line that has two terms is the purple line. That purple line is sloped, so it stays close to this function for quite a while, but then not for very much longer. The next one is the black line. The black line, unlike the purple line, the black line curves a little bit, so it stays close to the correct line for a longer time, even longer. The other red line, this red line, that stays closer, even closer to the correct red line. So this red line stays closer than the black line does, and closer than the black line does as well. So that's kind of cool. Now you'd have to have an infinite number of terms though to stay infinitely close to the correct graph forever. All right, well, that's cool. So let's go ahead to the next topic, which is relations. So any questions about the extended binomial theorem? Do you know how to extend the value of n choose r to values where n is u and any real number instead of just an integer? Okay, perfect. Okay, let me review about that because some of you weren't here when I started that. Okay, well, I accidentally stopped the whole meeting. And we're gonna have to restart it all and go back again. Sorry, just a second. There we go. Okay, let's go back to here. Go back to there. Go back to there. Go back to there. Join. We started it. That's kind of like have you ever taken the wrong exit on the highway? There we go. One time I took the wrong exit. Well, I almost missed my exit, and then I suddenly realized it. I turned at the last minute, and I actually drove off the edge of the highway by accident because I was so close to the thing. I didn't have an accident, thankfully, but I actually went over the curb a little bit. And then I realized next time if I miss my exit, I'm just going to go ahead and miss it and drive an extra mile instead of risking my car spinning out of control. Because there's probably a lot of people who've died because somebody realized they missed their exit and it was too late, and then they tried to take it. Anyway. Okay, well, so we're now going to just quiz you real quick about this. So what is 3 choose 1? We're going to use the extended definition of it, not the original definition. So what is 3 choose 1 according to the new definition of the combinations formula? Okay, I just realized I've got to. This has an echo unless I leave the audio on a computer. There we go. 3 choose 1 is what? How many terms will I have on the top of it? How many terms will 3 choose 1 have on the top of it? We'll have 3 or we'll have 1?
3.
No.
1.
1, right. So it's just going to be 3. And what number will be in the bottom of it? 1 close. 1 what? 1 factorial. Yep. Now that's all. So now this is not the same way that we defined it with the ordinary things. Previously, we would say 3 times 2 times 1 divided by 1 factorial times 2 factorial. So previously, you would say 3 choose 1 is the same as 3 on top, 3 factorial on top. We're choosing one of them, and we're not choosing two of them. So it's 3 factorial over 1 factorial times 2 factorial. But according to the new, more efficient definition, we don't even worry about the 2 or anything like that, because the 2 cancels into the 3 factorial and just leaves you with 3. And we just have 3 by itself over 1 factorial. So what is 4 choose 3 factorial? I'm sorry, not factorial. What does 4 choose 3 by itself? According to the new definition. How many terms will it be on top? No. The number of terms on top of the new method is the same as the number at the bottom of it. So 3 terms on top. Beginning with the 4, then you'll have 3, and then you'll have 2. And what goes on the bottom?
3 factorial.
3 factorial, yep. So the bottom number of the formula is the factorial that you have on the bottom. And the bottom number is also how many terms you have on the top as well. So they'll always match. You'll always have 3 terms on the top if you have 3 in the bottom, and you'll have 3 factorial in the bottom underneath the 3 terms on the top. And let's see, what is 3 choose 4? Now, this is something you can't do with the ordinary method. You can do it with the extended method. How many total terms will you have on top? 4. And you have 4 factorial on the bottom. So you'll start with 3, and then you go 1 less, and then you go 1 less, and then 1 less. So you'll have 3 times 2 times 1 times 0 over 4 factorial. And what's the total result of that? 0. So if you have an integer on top, you'll always end up with 0 if the bottom number is bigger than the top number. So, but what if you don't have an integer on top though? Like what is 3.5? Whoops, why did I write 3.4? What is 3.5? Sorry. What is 3.5 choose 4? You'll still have 4 terms on the top, and you'll still have 4 factorial on the bottom. What will the 4 terms be on the top though? Okay, let me go around the class. Okay, is Monty here? What about LaShawn? LaShawn, what is 3.5? It is just 3.5, right? Okay. Who's next? Zoe, what is 3.5 minus 1?
2.5.
2.5. Okay, perfect. And Isaac, what is 2.5 minus 1? 1.5, correct? And Colin, what is 1.5 minus 1? Correct. Good job. So that has 4 terms on the top. Each one of them is 1 less than the one before it, and you have 4 factorial on the bottom. Okay, good job. Let's go ahead and do one more. What is 1.5 choose 4? What does 1.5 choose 4? So first person would be Ignacio, however you say that. What is 1.5? It is just 1.5, right? Okay, then Caleb, are you here?
Yeah.
Caleb, what is 1.5 minus 1? Okay, good job. And then Arturo, what is 0.5 minus 1?
Minus 0.5.
Correct. And then Taylor, what is negative 0.5 minus 1 more?
Negative 1.5.
Correct. Correct. Good job. That was the hardest question. Okay, then that's going to be over 4 factorial, right? So there we go. I guess last 2 of you just got lucky. Okay, nice work, everybody. So now we know that. Now let's talk about relations. So what are relations? Relations. Did you know the book actually spends like half an entire chapter about the relations, and then it finally gets to one super critical kind of relation called equivalence relations. We're just going to talk about the basics, and then we're just going to explain what an equivalence relation is, and we're going to leave out all the fancy stuff. The book talks and talks and talks forever, basically. Because it's trying to show you how important they are. But you don't have to learn all that stuff, though. So relations, I'm going to use singular and just talk about one relation. It could be an arbitrary one, so it could be all relations, but a relation R on a set A. Okay, there's 3 properties of it. So basically, what is a relation R on a set A? It's really just a set of ordered pairs where each where each value is from A. Or from, I could say is in A instead of from A. Is in A. So it's a set of ordered pairs, and I'm gonna say it in a more mathematical way. It's a set of ordered pairs. I'm just gonna say like A comma B, where each value is in A. I could cross that out and just say where A comma B are in A, like that. So that's a more efficient way of writing it without as many words. So a relation R in a set A is a set of ordered pairs where A, B is in A. So for example, here's an example of relation. If A equals the numbers 1, 2, 3, then I could say the relation is the points 1, 3, and 2, 3, and 3, 1. So do you see those 3 points? 1, 3, 2, 3, and 3, 1. Each of those 2 coordinates of each point comes from the set A. Notice the set R has the elements of the set R are not numbers. They are pairs of numbers. And the order matters, like the X and Y coordinate is different from each other. So a relation on a set A is a set of ordered pairs where both of the numbers in the pair are in the set A. So we would say this, we would say notation. We would say that 1 is related to 3. Now I'm going to just have fun with this, okay? So let's say that the relation is liking someone. Liking someone. So person number 1 or player number 1 likes player number 3, but they do not like player number, and then person number 2 likes player number 3, and player number 3 likes player number 1, but which people don't like each other though, according to this relation? So let's just say R is called let's just say this is who likes each other on a certain team, where if A is B is in the set, that means that A likes B. Hold on. So R equals liking on a team where A or B means A likes B. So you can almost think of many relations as just being like relationships in real life, whether people are friends with each other or not friends, for example. So person number 1 likes person number 3, person number 2 likes person number 3, person number 3 likes person number 1. So I'm going to ask you a quick question. Who's the only person who doesn't like person number 3? No, person number 2 does. There's one person who doesn't like person number 3. Yep. So person number 3 doesn't like themselves. They must be like insecure or something. So 3 doesn't like themselves. That's what we can observe, right? And who's the most popular person? 3. Right. So 3 doesn't like themselves, yet they are the most popular. Because everybody else on the team likes them. Because everyone else. So remember, you might not like yourselves, but maybe everybody else likes you the most. Because everyone else likes them. In fact, maybe sometimes people actually do like people better that are not self-centered. What about player number? What about who's the least popular player? 2. Right. So 2 is least popular. 2 is least popular. Who likes player number 2? No one. No one does. Not even themselves. Now, if I wanted to have a little bit more fun with it, I could add the point 2, 2 into the set. So if I put 2, 2 into the relationship, what does that mean? 2 likes player 2, but nobody else does. So let me go ahead and add that in. If I put 2, 2 into the relation, then I can say 2 is the least popular. No one likes to but themselves. Except now, actually, though, now they are not the least popular anymore. Guess why? Because now they're just as popular as player number one is actually. Because now there's one person that likes player two, and there's one person that likes player number one. So they're actually both just as popular. Because there's the only person who likes player number one is player number three. So I guess I can't say they're least popular anymore, but so there's two that are least popular. Who are the two least popular players now? One and two, right? So one and two are the least popular, and that's because only one person likes each of them. Okay, so now you kind of understand the idea. So now I'm going to teach you a couple of properties that relations can have. One property that a relation can have, it doesn't have to have it, but it could have it, is called the reflexivity. Reflexive. If a relation is reflexive, if a relationship is reflexive, that means that everybody is related to themselves. So like that's, for example, genetic relations. Everybody is a relative of themselves, right? Like you're related to yourself, is that right? Technically, I guess you'd have to be. You're 100% related to yourself. Like you might be 50% of your parents' genes, 50% of your the other parents' genes, but you're 100% your own genes, right? So you're definitely related to yourself. So, okay, let me go start a new hybrid. So a relation is called a reflexive relation. The definition of that. Now, by the way, definitions sometimes use the word if and only if. That just means it's the definition, and if the definition is true, then that's called that. And if it's not true, then it's not called that. And it works in both directions. So R is called a reflexive relation if and only if for all elements of the set A, the point AA is within the relation. So is there a way to simplify what that's saying in a little bit more of an easy way to understand? What does that mean? R is called a reflexive relationship, is defined as if and only if for all elements in the set of things or people or whatever, that the point AA is in the relationship set. What does that mean? So in other words, this means A is always related to, a related could be liking or whatever the relationship is talking about, friends with, enemies with, whatever. This means A is always related to itself. Itself or himself or herself, whatever. I'll just say itself. So this means A is always related to itself. So that doesn't happen with some relations. So not all relations are reflexive. Like, for example, the one that we just talked about before was not reflexive because some people didn't actually like themselves. So let's give an example of one that is reflexive. So can anybody think of a relationship in the real world that would be reflexive? That everybody would always be related to themselves according to that type of relationship. What if we defined R is equal to being the same age? That would be a certain type of relationship between people, right? In this case, if you define the relationship as being the same age, is that relationship reflexive? Is all people in the set A, is it possible for anybody to not be the same age as themselves? No, it's not possible for you not to be the same age as yourself. So this means if R is equal to being the same age, then that means that therefore any person would always be related to themselves because A has to be the same age as itself, right? So let's just say they had 3 players on a team. Player number one. Okay, let's say A is equal to player number one, player number two, player number three. Then the relation, if the relation is being the same age, then you'd have to have player number one be included in the relationship with themselves. One would be related to one, two would be related to two, and three would be related to three. That's totally for sure, even if you had no idea what their ages actually were. The only thing you know is player number one for sure is the same age as player number one. Player number two is the same age as themselves. Player number three is the same age as themselves, right? Or person number. Now, can you give me an example of when that maybe wouldn't actually work? What if there's 2 player number threes? But that couldn't happen though, because the elements in a set have to be well defined. You can't really say, you can't say that 3 could be 2 different things. It only can represent one thing. Okay, well, by the way, if you do have a team that has 2 players with the same number on the field with the same jersey number, is that even allowed during a game? Because your number is supposed to be different for everybody who's at least playing right then. But okay, so there's a relation 1, 2, 2, 3, and you could add some other ones into it, but the only ones you know for sure that would be the same age as themselves are those 3, right? Okay, well, can anybody think of one more example of a relation that would be reflexive in the real world? What's a relationship that you could have with other people or that things could have with other things that would be reflexive, where everything would always be related to itself?
Hobbies.
Pardon me?
Hobbies.
Hobbies? Yeah. So you could say the relation would be like, you'd have to maybe define the hobbies in some way, but you could say like, are you interested in, yeah, we could say the hobbies are, do you have the same hobbies, I guess? Do you have the same hobbies with our, yeah, because everybody would always have the same hobbies as themselves. Yep. Right. I'm not sure if it'd be kind of hard to define the rest of the relationship, but it could be that part could be random, but yeah, but having the same hobbies would be a reflexive relation. Okay, now let's talk about symmetric. So what is a symmetric relationship? Or a symmetric relation? But it's not really a relationship like in the real world. It's just called a relation in math. What is a symmetric relation? A symmetric relation, now each of these is getting more complicated. The definition of a reflexive relation only involves one element of the set A. The definition of symmetric involves 2. So the definition of symmetric relation means for every 2 points that are in this set A, so R is a symmetric relation if and only if for every 2 points in A that if AB is in the relationship, then BA also has to be in the relationship. So this can't be something like liking somebody, because it's possible for person A to like person B and person B not to like person A, right? Like it like this that happens in the real world a lot. Like one person can like somebody else, another person doesn't have to like them back, right? But in a symmetric relationship, though, anytime one thing is related to the other thing through that type of relationship, the other thing is also related back to the original. So can anybody give me an example in the real world of a symmetric relation? Well, it's going to be a symmetric relation. Where anytime that one thing is related to this thing one is related to thing two also has to be related back to thing one as well. So if A is related to B, B has to be related to A because they're both points are in the relationship in both orders. And it's impossible for them not to be able to be in the relationship. Now, by the way, this is not saying that anybody likes anybody at all. So if you had a relation where nothing was related, that would actually be symmetric. So if I said there's an empty relation, and it just contains nothing, that's actually symmetric because this says if there's a point in R, then the opposite point has to be in R. So if there's nothing in the relation at all, then technically that automatically qualifies. Like, did you realize that every time that I've played in the NBA finals, I've always scored at least 80 points? That's a true statement. Because every single time I did it, that always happened. Right? Because I wasn't ever in it. So that technically that's true because every time I did it, which I never actually happened, I always scored at least 80 points. Right? In fact, every time I've ran for president, I've always won. So that's basically the word if can still be true even if nothing is actually in the set. So that's symmetric relation. Can anybody think of a symmetric relation that's not an empty relation? You should put that on your resume, actually. That you've won at least, scored at least 80 points in the NBA finals every time you've played in it. What's a non-empty symmetric relation? Well, just how about just being related genetically? Yeah, because okay, my pencil just broke. Let me try this again. Oh, maybe I need to pair it again.
So it's still parent and offspring. Something like that.
Well, but then the parent there might not necessarily be the offspring, though. Okay, there we go. It finally worked. I just had to minimize the app and then bring it back up. So related genetically would work, right? Because if like you're related genetically to somebody else, like you have the same mom or something like that, even if somebody else is adopted, if A is related to B, then B would have to be related to A because if A had the genetics from the same parents as B, then B would have to have the same genetics from parents as A, right? So that would be another symmetric example. So that's enough. That's two symmetric ones. Let's go to the third one. This involves 3 points at once. So this is called transitive. R is a transitive relationship. Or I shouldn't say relationship, I should say relation. R is a transitive relation if and only if, which by the way, the double F means if and only if. So R is a transitive relation if and only if for all 3 points A, B, and C that are elements of the set A. The if A is related to B, meaning A and B is in the relation, and if B is related to C as in the relation, then A also has to be related to C. So that means AC has to be in the relation. So if AB is in the relation and BC is in the relation, then A and C have to be in the relation. This means that this actually would also apply to the genetic thing as well, because if A is genetically related to B, and if B is genetically related to C, then A would also have to be genetically related to C. So an example of R could be genetically related. Okay, can anybody give me another example of transitive things that would not be genetically related though?
Like you go dad to son, something. Parents are plays.
Dad to son, son to mom. If you're a parent of somebody, so they're saying if you're a parent of somebody, so the relation would be you are a parent of someone. Is that right? Or you're a child of someone, which one would it be? You are a child of someone. So you're saying like if A is a child,
If A is the dad. And then B is the child, and C is the mom.
well, but that's a different relationship though. Being a dad or a mom can't be the same thing. The relation can only be like one thing, like A is a child of B. It can't change from being like A is a dad of B and like A is a mom of B. You could say a parent though. Yeah, so you could say the relation is defined as A is a parent of B. So no, that would not work because that would mean that if A is related to B, that means A is a parent of B. If B is related to C, that means that B is a parent of C. So that C would be like a grandchild.
So it has.
Yeah. But can anybody else think of a transitive relation? How about strength? How about this? A is stronger or faster. How about faster? A is faster than B. Would that be transitive? So if A is faster than B, we could say A is related to B. That means A is faster than B. And if B is faster than C, we'd say B is related to C. So if A is faster than B and B is faster than C, then would it be possible to draw the conclusion that A is faster than C? Yes, that would be logical. Because if they can run faster than B and B can run faster than C, then obviously A can run faster than C too. So if running faster would be a transitive relation. Okay, perfect. And then basically if a relation has all three properties, if a relation R is reflexive, symmetric, and transitive, then it is called an equivalence relation. And equivalence relations are very important kinds of relations. And the book talks for a whole section about them, and it works up for like 4 sections before that, just getting to that point. It's called an equivalence relation. Sorry, I guess I don't need to add anything else. Because we're almost out of class time, so I can't really tell you an example of an equivalence relation, but if it has all three properties, it's called an equivalence relation, and you can use it to partition sets into different classes called equivalence classes. So that's all for us today. So just be ready to come back again bright and fresh on Monday, and hope you have a happy Halloween. And by the way, let me make sure I get the rest of attendance taken care of before you go. So let me stop recording, but on your way out, I need to make sure I check you off again because I only have like 4 people checked in. Because